So since we're considering when we will find an induced current, let's look at this example and let's try to figure out which of these cases, and there might be more than one answer, will give us an induced current going through that loop of wire. So press pause, read through this, take some time to think about it, and choose all the answers that you think might apply. Well, Faraday's law tells us that when the magnetic flux through this loop changes, then we will have an induced current. So how can we change the flux through this loop? Well, I can change three things in order to change the flux. I can change the strength of the magnetic field. I can make the magnetic field bigger or smaller. And to make the magnetic field bigger, I could move the magnet closer to the loop. So A would increase the magnetic field passing through this loop, which would change the flux through that loop. We also could change the area of the loop. If the area of the loop suddenly gets a lot smaller, the flux through that loop would be a lot smaller. So by changing the area, I would be changing the flux through that loop. And then finally, since our magnetic field is a vector, and roughly from this north pole, it's going to be coming out and to the right, if I take this loop and change the direction that it's oriented, like maybe I orient the loop like this. If I have the loop oriented horizontally like this, then none of that magnetic field, which is directed horizontally, will pass through the loop. So the orientation of the loop also affects what the magnetic flux will be. So the first three definitely will cause an induced current because they will cause a change in the flux of magnetic field passing through this loop. For D, I just meant like you just rotate it like around in this direction, almost like a steering wheel. That's not going to do anything to change the flux. So this would not change the flux, the magnetic flux, which means it would not induce a current. So let's look a little bit more at magnetic flux. We're going to define magnetic flux just like how we defined electric flux a long time ago when we learned Gauss's law. So the Greek letter phi means flux, and then sub m because we're talking about magnetic flux. And it just measures how much magnetic field passes through a surface. So if I have a magnetic field directed up like this, and I have a surface that has a certain area, I want to know how much magnetic field passes through that surface. It's going to depend on how strong the magnetic field is, how big the area is, and how the area is oriented with respect to the magnetic field. So here's our equation that lets us calculate magnetic flux for a uniform magnetic field. Uniform means that the magnetic field has the same strength everywhere on our surface. So we're calculating the magnetic flux. We're going to take the dot product of the magnetic field with the area vector. And remember, we introduced the area vector back when we were looking at Gauss's law and electric flux. So let me just remind you what the area vector is. It's a vector. Don't let that scare you. Just because it's a vector, it's not scary. Remember, vectors have a magnitude and they have a direction. In this case, the magnitude of this vector is just the area of our surface that we're talking about. And the direction of our vector is just the normal to the surface that's shown here. So we take that vector and dot it with the magnetic field vector. Or if you don't like a dot product and you don't like seeing equations that have vectors in them because it scares you, that's fine. All you need to do is take the magnitude of the magnetic field, the magnitude of the area, so just how big is the area, times cosine of the angle between these two. So that's the angle between the magnetic field and the area vector. Or you can think the angle between the magnetic field and the normal to the surface, because these two things are in the same direction. So that's how we can calculate the magnetic flux through any surface, as long as the magnetic field is uniform everywhere on our surface. What if the magnetic field is not uniform? Well, then we have to integrate. So to take the total magnetic flux, I'm going to integrate over the whole surface, be dotted with dA, where dA is a tiny little chunk of surface. It's a tiny little bit of area. And if you don't like the dot product just tells you, take the magnitude of B, how strong your magnetic field is, take the magnitude of that tiny little bit of area, and multiply by cosine of the angle between the magnetic field and the normal to our area there. So we chop our area into chunks that are so small that we can say on that tiny little bit of area there, we can consider that the magnetic field has one single value. And then you do that for every single area, and then you add them all together, and that's your integral. So we'll do practice on that in a second. The units that we're going to use for the magnetic flux are called Webers. 1 Weber is equal to 1 Tesla meter squared. So we get the Tesla from the magnetic field and the meters squared from the area. Multiply those two together, we get the unit of magnetic flux, which is Webers.